get started. Yes?
Is there any way that we could use at least some of today to review stuff that's going to be on the test? Because I don't understand a lot of the concepts, and I've talked to a lot of people, and I might be wrong, but I don't think I'm the only one.
Okay. Yeah, definitely.
Okay.
My plan was to review the homework due for today, and then actually open up for questions.
Okay.
So that's what I was hoping to do. All right. So let's go ahead then and start looking at problem 312. What's the best way to do lights here? That's probably two. How's that? All right. So problem 312. I'm going to walk through it a little bit slowly, more slowly than maybe future ones, because I know that you're kind of getting used to putting this into Excel. So let me make sure that I turn on my little open solver thing again here. Turn that off. I'm back on, which is annoying. But that's what it appears to need to do for this machine. There we go. So we've got our stuff in here. All right, so what I'm going to do is I'm going to use three variables, E, S, and D. I would encourage you actually not to do this in your spreadsheet because you're not limited to single variable names. So what you should do is use names that are meaningful. So what does the E value represent? The economy. So make it and S stands for, and the D is, and maybe we could even be more specific and put number of these units, right? Here. So don't feel like you need to be terse when you're making these Excel spreadsheets. It will make them more readable. It will make them more easy to understand later instead of waiting what was E again? What did that mean? And so forth. And then what are we trying to do? What's our goal? Maximize profit. So I'm just going to write that out here. What profit? So what is the profit for this problem? 63 times B1 95 times B2 plus 135 times B3. All right? So now it's a lot more clear what we're trying to do. And now we can put our constraints in here. And so and I would encourage you to name these constraints as well. Make sure that you're saying what this equation that you're putting in here represents. So the first one I have is that B1 plus B2 plus B3 has to be less than or equal to 200. What is that constraint representing? What's that? Okay, so we can write that. Number of fan blades. Right, and make that a little larger. So it's really clear what we're doing here, right? Make your models understandable to you, not just when you're writing it, but when you come back to it. That's the whole point of these models, is that you can revisit them, that you can edit them, that you can find more information. Things change and you can update them. If you have them documented like that, it's possible to do that. If you just do it in the moment, you might as well just write a whole new model rather than try to interpret it, because it's going to be... And for the size of problem that we're talking about today, writing a new model isn't that big of a deal. But when you start talking about life applications, that's not such a feasible thing. The next constraint I have is B1 plus 2 times B2 plus 4 times B3. What was that constraint? Had to be less than or equal to 320.
Cooling coils.
Okay. Number of cooling coils. And then the last one I had was 8 times B1 plus 12 times B2 plus 14 times B3. Had to be less than or equal to 2,400. And what was that constraint? What's that? Hours. Okay, and we don't have to put our logical constraints into this one, right? The computer already assumes that those logical constraints are going to have to be enforced. So no negative values for our variables. So let's go ahead and make sure that we then enter this into our model. Our objective is to maximize our profit. So I put the profit in that objective cell. And our variable cells are these 3 values: the number of economy, standard, or deluxe units we want to build. And then our constraints on Wednesday last week, I showed entering each constraint one by one. But I want to show you a little bit faster way that we can do it. I can put the left-hand side of constraints here, and they're all less than or equal constraints. I can do this. If some of them were less than or equal and some of them were greater than equal, I couldn't do this because I can't change. This less than or equal is only for my benefit. It's not for the model's benefit right here. So this is the left-hand side of those equations. This is the right-hand side of those equations. And I can add that one set of constraints rather than doing 3 individual constraints. It means the same thing. All right. And I am going to click on this now. I'll put the sensitivity analysis. That's going to become important in just a second here. All right. Yeah. No. And let's go ahead and solve this. There we go. So we have our solution right here, right? We have that we should make 80 economy units, we should make 120 standard units, and we should make 0 deluxe units right here. All right? So that should have been hopefully pretty straightforward, because this was just building a model like we've done before. There's nothing fancy here. We can see what our max profit is. That's $16,440 right here. And so we get part A from 312. Hopefully pretty straightforward. I hope that was not too difficult for anyone. All right. Before we even look at the sensitivity sheet, can we answer part B, which was which of these constraints are binding? How? Yeah, we can, whoops, wrong direction here. We can look at these values right here, and we can see that they are jutting up against our constraint values, our right-hand side right here. There's no more room to add any more fan blades or cooling coils, because if we did, we would bump above this. So these are binding constraints because of that. But this value right here, 2080, we have a lot of free hours available to us. This is not a binding constraint. We could have lowered this value from 2400 down to 2100 and still it wouldn't be a binding constraint. Right? So even before we look at our sensitivity analysis, we can identify that about our system. It also comes out very clearly in our excuse me, in our sensitivity analysis. Let me see if I can make that a little bit bigger here.
Is that always going to be the case where the final value and the right-hand side value will equal each other for two of them?
If,
that will be the binding ones?
No, it could be. You can just have one constraint that's binding. If you think about if you draw it graphically, and the binding constraint intersects at a y-axis or an x-axis, only one constraint is binding then.
Okay, so
and you can have more than two binding constraints.
Right. So then, is it possible, I guess what I'm asking, is it possible to have a binding constraint that is not equal to the right-hand side value?
No.
Okay. It
must equal to the right side value. Otherwise, there would be slack or surplus, depending upon the constraint type, available for you to it's not up against that constraint.
Okay.
So that's by definition, it has to equal that. Now, sometimes it might look like it's a tiny bit off because of the way that computers store floating point fractional values inside of them. But that's a computer issue. That's not. That's theoretically the fact that it's binding means it has to equal that right-hand side. Okay. We can see that also here from our sensitivity analysis. Right? How can we tell from our sensitivity analysis that these two are binding constraints? Yep, and even more importantly, is that they have a shadow price. A shadow price is the same as a dual. Okay? So because they have a dual price, that means that they're binding. There is no dual. We can't move this third one and improve our objective function because it's not binding. So these are binding, therefore they have a dual. This one does not have a dual because it is not binding. Yeah, Ross.
What is the dual mean?
Okay, so the dual, remember, is that for every one change in our right-hand side value, we will see this much improvement in the objective function. So what that means is if we increase this value from 200 to 201, we would expect the objective function to increase by 31. Let me demonstrate that rather than make that theoretically. It's a lot easier when we have the computer do it, solve it quickly, right, than go through the simplex method, right? So if we change this from 200 to 201 and we resolve it, we expect, let me just copy this value real quick here over here. Fine, 16,440. I didn't want the bunk. I wanted the value, not the equation. Right? If we increase this and I resolve this, it's 31 larger right there. Okay? So that's exactly what it's telling us, is that if we increase this value by 1, we expect it the objective function to increase by 31. If we increase this by 1, we expect the objective function to increase by 32. Likewise, if we decrease this value by 1, we expect the objective value to decrease by 31. And if we decrease this by 1, we expect the objective value to decrease by 32. And it is linear, so if instead of changing it by 1, right, if we change this by 10, because that will be easy, 210, right there, how much would we expect it to increase by? If we increase this value by 10, how much will the objective function increase by? 310, because for each unit it increased by 31. So 31 times 10 gives us 310. So if we resolve it, we can see, well, let's make sure, B5 minus C5. 310 right there. Okay? Yes?
So how can the hours be zero if, can you just keep decreasing hours and keep the same price? Is that?
Yes. That's what that means. That we can change the value of this right-hand side, and it's not going to change our objective function.
Okay.
Up to, and now this is where these two really come in important right here, your allowable increase and your allowable decrease. This limits how much or how little you can make a change to these right-hand side values right here, how long that dual becomes valid. So the range that we can do that is we can increase for this first right-hand side, we can go from 210, we can up it by 70. So that means as long as it's no more than 280, this shadow price holds. Also, we can decrease it by 50. So it can go down to 160. So in that range of 160 up to 280, that shadow price, that dual, holds true. Any range in there, we're going to do 31 units change to our objective function for each unit change in our right-hand side here. Okay, so you can see that is true for here. And now this basically represents infinity, right? We can increase this value right here. We can increase our hours however much we want because it was a non-binding constraint. We can go and go. We could have 1,000,000 hours. We can have a Google, right? That's a Google. We can have a Google number of hours, and it's not going to change our objective function. What matters, we start it to become a binding constraint when it drops 280 below its current value, right? 280 below that 2400 there exactly hits this 2120 mark right here, right? And it becomes binding. And then if we drop it further below that, now it is going to affect our objective function. It is going to cost us something to drop those hours below that 280. So these two here are giving us a range within which this shadow price is valid. So it's not unlimited. We can only make those changes in that limited range. Yeah?
Is something like this going to be on the test and we just have to, like, you give us this and we just have to interpret it type thing?
For the test, yeah, so I might give you this dual and I say, what if we increase the final value by this much? How much is the objective function going to be expected to be changed? Mm-hmm. All right. So where did I put that? Okay. So let me turn this back then to what it was, so we can keep answering 3-2. This was 200, right? All right. So we've identified our objective function and solutions, our constraints. Part C was which one is not binding. We've already said that. How much slack is in this constraint right here? How do we figure out what the slack is? There's two ways that you can do it. The complicated way is subtract the right-hand side value from its current value, right? That's its slack. Or you can just look what that allowable decrease is. That's how much we can lower it before it becomes binding. So that's what our slack is. All right. All right. And then part D, I think, was what if we were able to profit from our deluxe motors more, right? I forget what the exact was, maybe another $15, $150, okay? We can answer that from this chart right here. The answer is no, okay? We're not going to change our solution because we can increase that profit by 24 before we are going to see a change in our objective function. We have it until we have that, we're not going to change our objective function. Because remember, these ranges here are different than these ranges here. These ranges are how much we can modify these coefficients right here in our objective function. 63, 95, and 100. So as long as the coefficient is between 51 and 78.5, I've just added these values here, or this one is between 64 and 103, and this one is less than 159, there's no change in the optimal solution. We only would change the optimal solution if we went outside of these ranges right here. Right here. And so by adding only 15 to go from 135 all the way up to 150 does not keep us, does not go outside of these ranges right here. And so as a result, we don't change our optimum solution. And if you're not sure, you can always check, right? That's the nice thing, right? We can add it. We can change our objective function here to be from 135 to 150. Resolve it, and you get the exact same solution. All right. Oh. Yes. You can't undo through a solve. Okay, solve. Okay, so that was question 312. Then question 313 continued on with this same model, right? So you didn't have to do a new model. It was asking more questions about this same model right here. And it asked what the ranges of the coefficients were. And that's where you look at these values right here. What you're going to do is you're going to take your coefficient value, for instance, here, 63, and you can add 12 to it, and you get 55. You subtract 15.5 from it, and you get, wait, I can't add right, 75. You subtract 15.5 from it, and you get 47.5. So the range of this coefficient right here is between 47.5 and 75. If it's within that range, it's not going to change your optimal solution. You can do the same thing here, and you get between 7 and 126. And here, it's less than 159. Okay. Yes?
What's the difference between the final value and the objective value?
Yeah, let me be careful about that. The final value is the value of this variable that solves your maximization or your minimization problem. The objective value, let me rephrase it, call it the value of your objective function is not the value of each individual variable. It's this value right here. It's that 16,440. Right? So our objective function incorporates all of our variables multiplied by some coefficients here to get some value for our final solution. So that we're talking about multiple values, the values of each of these individual variables and the value of this function that we're maximizing in this case right here. So these directly inform this.
So the objective value on the other side, on the other sheet, was just the coefficients in the objective function?
Yes.
Okay.
Thank you. I didn't realize you were referring to this column here. Yes, so this is the coefficients in the objective function. And this is the value of the variables that maximize our objective function. All right. So part B asked, what happens if you make changes to the coefficients, right? So if we change those real quick, we can see. What we can't do is we can't use this sheet to interpret the answer to that problem. Why can't we use this sheet to interpret if we make those changes to those coefficients? Yeah.
Becomes a different problem when we change the coefficients. So we change our baseline, so we can't use the same.
But I want a little bit more tightness in your answer. I just said that if we change the objective value of that first one from 63 to 70, it would still be valid.
Or we change them all.
Yes, right? This is only true if we change one variable. As soon as we change more than one, our analysis does not reflect multiple changes. Right? So that's why we have to go back here and actually change them in our objective function. So if my notes are correct, it said to change it from 63 to 69 here, and from 95 to 93, and from 135 to 139. And when we resolve it, notice we say that this is the same solution. And what we mean by that is the values of our variables don't change. We still have 80 economy, 120 standard, and 0 deluxe units that we're going to produce. Almost, of course, this value has to change because we're multiplying these values by different coefficients. They're going to be different. This objective function is going to be different. But what we cared about, right, is how many should we produce? The answer to that question was unchanged. We produce 80 of these, 120 of these, and 0 of these. Okay, so that's why we say the solution is unchanged, even though this value changed right here. Okay. Excuse me. So for part C, I should probably turn this back real quick. So it was 63, 95, and 135, right? Resolve it, look at our sensitivity analysis. For part C, now what we do is we use these right here to tell us what the ranges are for our right-hand side values to have the where we don't change our binding constraints. So we can add 80 here, or we can subtract 40. So we get a range of 160 to 280 there. We have 200 to 400 for the second one, and 2080 or larger for the third one.
So, I know it doesn't really matter because of completion, but on the test,
Mm-hmm.
can you specify if, like, we go back to the old values and then do, like, because on, like, problem C, I, like, asked a new question, and I just kept it with the same values
Okay.
from the last time?
Yeah, yeah. I definitely would. I definitely would. Yes. Yeah, I can totally see how that would be confusing.
Yeah.
Part D asks, what happens if we change the number of fan blades from 200 to 300, right? Is that going to change our binding constraints? And the answer is yes, because our limit was 200 plus 80 right here, right? So so if we put in 300, we would see different binding constraints because of that. Yes.
So you said in the last problem, if you changed multiple coefficients of the objective function,
Uh-huh.
you couldn't use that sensitivity analysis.
Right.
If you were to change multiple right-hand side values of the constraints, would you still be able to use that?
No.
Okay.
We're only looking at a single change at a time. Mhm.
Okay. Should we know how to solve something if multiple constraints are changed?
You would just have to rerun the
Okay,
solver.
just rerun.
Mhm. That's the only option you have.
Okay.
Do we need something, we won't need something to run this for the exam?
Correct. You won't, anything that requires a fully computed model will be provided for you with the model and the sensitivity analysis. So it'll be an interpretation of the results rather than a computation of the result. You may have to do a step in the simplex method, but not the full simplex method. Then we added 2 additional questions, right? A part E and part F that weren't in your textbook, which was how far does this coefficient have to increase in order for you to be able to start charging, building deluxe models? And the answer there is 24, right? You have to make at least a profit of $159 before it's worth building those deluxe fans.
Would it be at the 159 or above the 159?
It'd be at the 159,
Okay.
right? Oh, that's when this becomes binding, right?
Okay.
Depending, and so you can always double check, right? Let's change it. That's the beauty of this, right? We can always experiment and find out. 159. And we build 40 at that point.
It's the same as standard.
What's that?
It's the same profit,
It's the same profit.
because that's where they all understand.
Yeah, it was but we make a different set. All right. And then I'll just tell you for F, since I've already shown you the idea, that what you had to do for that last one is you actually had to modify the right-hand sides because there were multiple changes. One decreased down to 160, up by 80, and another by 20, and it ended up not changing any of the duals. But the only way you could figure that out is actually to run it and find it again. There's not a shortcut that you can say, oh, well, because these changed by this much, this is what the duals are going to do. Because it moves all those lines. Every single constraint is being moved, so that all their intersections are changing, all of their, which one becomes binding or not change. And so the only way that you can know for sure is to actually rerun the model. All right. Okay, questions about that, the homework assignment? Okay, can someone turn on the lights for me? I think we'll be done with this, and I'll switch to kind of prepping for Wednesday's exam. Okay, so the material in the exam is chapters 1 through 3 in your textbook, plus chapter 17, that online chapter. Those are what are going to be on the exam. So you will be expected to be able to do some things that hopefully feel old hat at this point, like being able to draw constraints on a graph and identify what the feasible region of the model is. You should be able to come up with the mathematical model. So being able to say this is a maximization or a minimization problem, what your variables are, and what the constraints are from that. So I can give you a word problem, and you can write down, this is what I would enter into my Excel spreadsheet in order to solve it. Okay? So you should be able to do that, and then you would just stop at that point. You wouldn't be expected to solve it as in this particular example.
Do we have to be able to state the
No, I expect you to just be able to go through them. Yeah, so go through all four, identifying your variables, identifying your goal, identifying your constraints, and then stating the equation for your goal in terms of your variables. Okay. You should be able to go through the entire simplex method. Now, I've said this multiple times, but I want to make it clear. You won't be expected to go through the entire simplex method on any particular problem. You will probably be given some partially completed one, and you say, here's what the next step would be, or to be able to interpret this value here reflects this meaning. If I give you an equation, you should be able to write the first tableau up. And if I give you a tableau, you should be able to identify this is what the next variable that's going to go into the basis for the iteration is. And this is which variable it's going to replace. And then you should be able to identify when the simplex method ends. So if I give you an iteration, you should be able to say this is the last iteration or not, because these values are either they're positive or not, and so we need to continue, or they're not positive, they're 0 or negative, and so we're done with the simplex method. But each of those can be done in isolation so that they don't build on top of each other. What I don't want you to feel like is I'm going to have to go through 7 steps of the simplex method, and I somehow made a silly arithmetic error on the first part of the first step, and that's just cascaded through the entire equation and has totally ruined my solution, okay? So I'm intentionally going to do it so that those types of errors can't percolate through the rest of your test, okay? But you need to be able to do each step along the way. Yes?
So the rule for ending is that the coefficient should be negative and the solution should be positive?
So no, you can have a negative value. So remember, the reason when you stop your Cj minus Zj, you've got that set of values right here. They all have to be less than or equal to 0. That's your stopping condition. The reason why I said your value, your objective value, let me be more specific, the value of your objective function at this iteration in the simplex method, this can be any value when you stop. The reason why that's true is to think about how we handled doing a minimization problem. Right? When we did a minimization problem, we transferred this into a maximization of the opposite of this. And so in these cases, you're oftentimes going to have a negative value there. And so you can't look at this value and say, oh, it's negative or it's positive, therefore we're done. You can only look at these values right here. Yes?
So you will just end up with like the right answer
Mm-hmm.
in that. You don't have to convert it again at the end for a minimization problem.
Right. Well, so this would end up with a negative value because you made that transformation. And then you would undo that transformation to get back the minimization, right? Because you computed the negative, and so you would, the minimization would be the opposite.
Negative, but it's a negative. So
Yes, yes,
so you
yes,
have to-
yes. All right. So you need to be able to do each of those steps. Finally, you need to be able to do what we did today in class with understanding the sensitivity analysis. What is the dual? What does it mean? How are the ranges of the coefficients of the objective function? How are they bound? And for the dual, what range of values for those right-hand side constrain the dual? Yeah, so Nathan.
Do you ever need to calculate the dual manually?
You may have to calculate the dual manually. Uh-huh.
Would that go for the range as well?
Yeah. Because remember, what you're calculating is the slope of your objective function, and you're calculating the slopes of your constraints. And what you do is you see how far you can modify that objective function and still stay within the slope of those binding constraints. So you just remember we had something like, if we had an objective function that was 4a, so let's say we maximize 4a plus 5b. Okay. We said that the slope of this objective function, let me make it x and y just so it's easier. 4x plus 5y. The slope of this objective function is negative 4 over 5 because we did negative the x over the y value right here. And so that's the slope of our objective function. And if we have some constraints that look like 3x minus 2y has to be less than or equal to 15, this also has a slope right here. Right? And we do the same slope for it. It is negative 3, because that's our x value, over negative 2, which is 3 halves. And let me make a third equation, a second binding constraint. Let's make it 10x plus 9y has to be less than or equal to 150. I mean, I don't care what that value is, because we care about the slopes here. All right? And the slope for this one is negative 10 divided by 9, right there. Okay? And so we can see that this slope of our objective function, negative 4/5, is between negative 10/9 and positive 3 halves. So then what you can do is we can examine the coefficient of x changing, and we hold the coefficient of y constant. Coefficient of x, coefficient of y. X and y right here. Has to be between negative 10/9 and positive 3 halves. So we can just multiply both of these sides by 5 here, and we get whatever negative 50/9 is, and 15 halves. That's the range that this coefficient can change without changing our solution for x. And we can do the exact same thing for our y. Negative 10/9 is less than or equal to, now we're going to hold our x coefficient the same, so that's negative 4, and we're going to allow our y coefficient to change. And so here, what we're going to do, oh wait, this was supposed to be, yeah, that's good. All right, so I'm going to multiply this by cy. And then I'm going to multiply this by negative 9/10 to get cy is greater than or equal to negative 4 times negative 9/10. So cy has to be greater than or equal to positive 36/10. Right? Remember, I flipped from less than or equal to greater than or equal because I multiplied by a negative here. And then I unlike this case where I did both of these at the same time, I only did one side of this range of inequalities because this coefficient is on the bottom. It just is a lot easier for me mentally to do this separate steps rather than do it in one step. And so I had the same negative 4 over cy is less than or equal to 3 halves here. And we get negative 4 is less than or equal to 3 halves times cy. And then we can multiply by 2/3. So negative 8/3 is less than or equal to cy. And now I can combine these two together and say that negative 8/3 is less than cy, and cy is less than or equal to 36/10 right here. If you just switch those.
So would your final answer just be those two inequalities for
Yeah.
x?
Yeah, so if I only change x, it can move between negative 59ths and positive 15/2. And if I only change y, it can be between negative 8/3 and positive 36/10. Yes?
And the dual is just the slope of the line, right?
The dual is not the slope of the line. Because the dual is how much, the dual is related, is not related to these coefficients right here, right? The dual is related to these right-hand sides. The dual says if I change one of these coefficients, say I go from 15 to 16 right here, how much is that going to affect this new value?
So that you have to like taking two different points and then the difference in profit.
Yeah, so yeah, that's exactly what you would do. Is you would increase your right-hand side by some amount. Then you'd figure out how much the objective changed. And then you divide it by how much you changed it. Okay. With one tiny caveat. You need to make sure that when you make this change, you don't go beyond the range that is valid for that. Remember, because the dual has a range that you can only increase or decrease these values by a certain amount. And if you happen to increase it beyond that allowable amount, you're not calculating the right dual. So you need to be careful there.
Your answer says that 36/10 is less than CY, but then the final one you have it as greater than. I'm just confused by that.
Here. So, did I?
Aren't you multiplying? Oh, never mind. That's divided
I'm not seeing my error, but it's clearly wrong. You're right.
Well, does the signs change from one of them?
The change, yeah, because we multiplied by a negative here, but we didn't multiply by a negative here.
yeah, but it should have flipped. So it should change underneath that one. Oh, no, I see.
I'd have to look in more detail and but this, yeah, it's the right process. It's the wrong result. You would get most of the credit for doing the right process, but not the full credit because you missed the result. So I would not get a perfect today. And yes, yeah. If you have more questions, please feel free to stop by my office hours tomorrow.